Hey, AP Chemsters, this is Mrs. Vanderwaalte with the last installment of section 13.4, the integrated rate law. So we begin with problem number 16. And so here's our equation, here's our diagram. And the question we first start off with is, according to the following graphs, is this zero, first or second order? Well, it's definitely not a zero order because we don't have the right parameters, if you will. We don't have concentration versus time. So it's either first or second. So which one has a natural log? That would be first order with a natural log, but this is not linear. Remember how before, when we started this, that the natural log had to be a linear graph for that to work. It's not linear. So our only other choice is really second order, which does this fit the criteria? It's 1 over the concentration, and it does appear to be linear. Therefore, this is a second order reaction, okay? So let's go on to the next question. So what is the value of the rate constant for this particular reaction? Well, we have to know it is a second order. And the rate law, the integrated rate law for a second order reaction is this, 1 over. And so what do I do next? I plug in the numbers. Now again, just like before, you can pick whichever one you want. You can choose any of these values you so want. But this, again, this is the original one at time 0. So that is your A naught. But anything else you can use. So let's see what happens here. I went ahead and I chose the next one. You can pick whichever one you want, and I encourage you to. So I'm pick the last one and see if we end up with the same K value. So after this, I went ahead and I did my math. I found that 1 over 0.00625 is 160. Here, I'll just center it over here. And 1 over 0.01 is 100. I subtracted 100 from both sides, and then I just solved for K. So I subtracted, and then I solve. So K is 0.06001 over seconds. Okay? All right, so what is the half-life for the reaction? Well, if you recall, then it is a second order, and a second order half-life equation looks like this. So I need to know what the K value is, and I need to know what my initial value is. So here they are. And so notice it's 1 over seconds. And so notice what's going to happen. Seconds is going to end up on top, and the molarity kind of fizzles out. You kind of leave it, let it go. And when you do the math, I hope you get 1666. So with as many sig figs as they gave you, that's a pretty good number there. All right, I really like problem number 17. You really have to know your stuff to really answer this. So let's see what kind of information we can get from the description here. It says a decomposition reaction, the rate is observed to slow down. That's one of our big hints, all right? We're going to slow down here. The rate will slow down, and the reaction proceeds, and it is found to have a half-life reaction that depends on the initial concentration of the reactant. So which statement is most likely true? Well, what you probably need to think about first of all, is this a 0, first, or second order? Well, let's see. If it's a 0 order, all right, here's the half-life reaction. Well, according to this, it is dependent on the initial concentration. So that is true. It does depend on it. But will it slow down as the reaction proceeds? Go to page 5 for me and kind of tell me what this graph says. The rate remains constant no matter what the concentration of A is. Do you see that? So if A doubles and triples or whatever, what happens to the rate? The rate remains the same. So what if the concentration of A goes down? The rate remains the same. So 0 order as the reaction proceeds, because even though A is changing, it's decreasing, the rate remains the same. So let's go back to our question 16. All right, so here we are on page 16. And so does the rate slow down? The answer is no, it does. It remains the same. So it's not going to be 0 order. We can cancel that one out. Is it first order? Well, let's find that out. So here's first. And what is the equation for first order? Here it is. And does first order depend on the initial concentration? The answer is no. It's nowhere in the equation, so it's not dependent on the initial amount. All right, so it kind of leaves us with a second one. And here's the equation. And what's happening here, that yes, that it is dependent on the initial concentration. Now, does second order mean it's going to slow down as the reaction proceeds? And the answer is yes. Because if we go back and look at page 5, you can do that on your own, we see that it does change with the amount of A. So as the amount of A decreases, so will the rate. Okay, so the rate's going to go down as A goes down. So it does slow down as A goes down. So that makes a lot of sense to me. All right, so now we know it's a second order. Do these A, B's, and C's, which one makes sense for a second order? So is A plot of the natural log of the concentration of the reactant as a function of time linear? The answer is no, that's first order. A describes the first order. The half-life of the reaction increases as the initial concentration increases. So what happens if this number down here gets bigger? What will the half-life do? Will half-life go up if it's in the denominator? No, half-life is going to go down, so B's wrong. I'll cross that guy out too. A doubling of the concentration will result in a quadrupling of the rate. Now, this half-life reaction doesn't tell us this. This is not rate, this is a time. So if we go back to our original definition of what a second order reaction is, that is true. A doubling of the initial concentration result in a quadrupling. This is really the definition of a second order. So letter C is our answer. Let's go on to the next page. All right, so here's our last section of section 13.4, and it's the integrated rate laws for more than one reactant. And so how do you deal with this? Remember how we ended 13.3 that we had to hold something constant and see how it worked if you had more than one reactant? So what do we do here? What's an integrated rate law if you have more than one reactant, which is most of the reactions out there? Well, you have to purposely contrive the experiment so that you have one of the reactants have a much smaller molarity than the others, all right? So that way that order will determine, in a sense, the rate. So here, for example, if here's my rate law, and we have A, B, and C as my reactants, and there are some orders, first, second, or zero, or whatever, you're going to make sure B is bigger than A and C is bigger than A. All right, so then B and C don't change very much as relation to A. So the rate law is what's called a pseudo order rate law. Okay, so that's what that little prime number or prime symbol by that K means, a pseudo order rate law. So it could be a first order if that's what A is, or a second order if that's what A is, or a zero order if that's what A is. So then the simplification yields a particular order. So let's look at problem number 18 and check out what we mean by all this. So here's our reaction. We see that it's first order in A, second order B, and actually it's zero order in C. And how do I know that? Because C doesn't even show up here. So C to the 0 power is equals to 1, so we just leave it off. So C is a zero order. All right, so which one is in the smallest quantity? Let's check this out. A is about 0.01 molar, B is 3 molar, and C is 2 molar. So obviously A is the one in the smallest quantity. So the reaction started and the concentration of A decreases. So calculate K for this reaction. So what up here is telling us, if we contrive to have high numbers of B and C and only a small amount of A, then it's going to be whatever order A is. And if you look over here, A is first order. So to solve for the first order, solve for K if it's the first order, I'm going to go back to this equation, one that you've probably written down about 100 times. And by now, you probably can plug all of these numbers in on your own and solve for K. So why don't you go ahead and do that and see what you get. Why don't you pause this while you work out the problem. Okay, so how did you do? Well, this is what I did. I plugged in the amount at time t. I know it's 8 seconds later, and here's the original amount. I went ahead and I plugged in some numbers here. All right, so I have, come here. Here we go. All right, so here I have this value, so natural log of 3.8 times 10 to the third I got here. and I kept solving for K. And so hopefully this is what you got for K. K is 0.121 1/2 seconds. All right, having done that, we can now calculate the half-life of the experiment. We know it's a first order, so why don't you go ahead and work on this part. So here's the half-life. Plugged in my values, and here's my final answer. Now, does this answer make sense to you? It makes sense to me, all right, because what's the half-life? It's almost 6 seconds. So if we start off with 0.01 molar, where is it? Right here, 0.01 molar of A, roughly 6 seconds later, be 0.05 left, right? And then another 6 seconds later, you'd have 0.025 later. Well, if you looked at 8 seconds, okay, we had somewhere between 0.05 and 0.025 molar left. So that makes, or say 0.005 and 0.0025 molar left. And that makes sense. This number right here makes sense for this number right here. So now it says calculate the concentration rate after 13 seconds. Hey, I bet it's something just under 0.0025 because that's 2 half-lives later. Let's see if we're right. Go ahead and solve for A. So here we go again. This time we don't know what A is. Hopefully you've already done this and you're just checking your work. And oops, I left out a step. Here we go. All right, so I plugged in the values here. So how do you solve for A in this case? You find the E value of it, and there you go. And look at the answer. Oh my goodness, I'm a genius. Not really. Remember what I said? If it was 2 half-lives, it'd be under or be at 0.0025. We're at 13 seconds, so it's just under that. It makes sense. I love it when that happens. All right, so now what? Calculate. Oh, this is different. Oh my goodness. What am I supposed to do? Calculate the concentration of C? I don't know anything about C. Oh wait, I do. I know what the reaction is. Huh. So do you think I could set up a BCA table? I bet I could. Why don't you set up a BCA table and see where it takes you? Okay, pause this, work on it, and I'll be right back. All right, so I'm setting up my BCA. So what were my initial concentrations? Well, there they are. Now, what do I know? After 13 seconds, how much A do I have left? That much. All right, so what did I have to subtract this by to get this number? All right, so what is 0.01 minus 0.0021 equal to? And that is your point. I'll just type it in here, 0.0079. So that's how much change A had. So for every 2 A changes, what's going to happen to C? So what's twice this? So that times 2 is roughly 0.016. So now what's 2 minus 0.016? Oops. I'm doing it right now. I could probably do this in my head, but for some reason I'm not. 2 minus 0.016, and that's equal to 1.98. And that would be your final molarity. And what does this whole thing ask? I love this question, by the way. What does this mean? Because you had such a high concentration of B and C, it really didn't change all that much with A, did it? A changed a great amount. C and B did not. And so that's what this is showing you. Okay. Now what I'd like you to do as we conclude here, go to page 615 in your book, and you can fill out this all by yourself. So I hope you've enjoyed your time off here, and please think about chemistry, all right? Have any questions ready for Mrs. Blankenship, for myself, and I hope to see you guys during office hours next week. Bye-bye.